Welcome back. This is our last chapter of the semester, and we'll be talking about sleep, something that a behavior that we engage in a lot over the course of our lives, and talking about some of the factors that influence it, trying to describe the behavior, sleep as a behavior, changes in the functioning of the central nervous system, give you some theories of why we sleep, and then talk about some sleep disorders. So in terms of understanding sleep, it's important to kind of understand sleep in the context of our environment and how changes in our environment are associated with changes in our behavior. So if we look at our environment, we see that there are certain clocks or periodic changes that occur across the day, from day to night. We see that there's a certain portion of the day that's light and a certain portion of the day that is dark. And that occurs consistently over time. In addition, what we see is that there are changes that occur across the year. So that in summer there are longer days in the northern hemisphere, whereas in winter the days are shorter and nights are longer. So there are these consistent environmental changes that occur that evolution has been influenced by our evolution. And these things are likely associated with behavioral changes. So these are consistent, cyclic changes in the environment that are likely to be associated with changes in behavior. So let's look at some of those behavioral changes, if they are associated with these. And first, what we see within a day, we see circadian rhythms, or where levels of activity change across the day. Now, if we look at a rodent, who are typically nocturnal animals, what we'll find is that they're not very active from 6 in the morning, 6 a.m., till 6 p.m. They're largely sleeping. But from 6 p.m. to 6 a.m. overnight, when there's dark portion of their schedule, or their daily light-dark cycle, we see that there's a great amount of activity. And so what this graph represents is each line represents a single day's activity, whether they were running on a wheel, they've counted wheel revolutions, or each one of these could be a movement in the cage or something like that. But what you'll notice is that when the lights come on at 6 or go off at 6 p.m., that's when the animals become very active. When the lights turn on here at 6 a.m., we see that they start to become less active. And the activity is fairly well contained within this dark period for these animals. So these circadian rhythms are an important relationship between the change in the environment, the light-dark cycle, and the behavior, the activity level we see of the animal. And we see this not only in rodents but humans. Many other organisms show this change in activity level across their light-dark cycle, referred to as their circadian rhythm. Now, in addition to daily rhythms, we see that there are changes that occur across the year, or we call these circa-annual kinds of rhythms. And what these can be controlled in terms of their control is the amount of light or dark available in the environment. And so, for example, if we look at hamster mating over the course of the year, hamsters only mate at certain parts of the year, and that's going to be related to an abundance of certain food resources and those things. And what we see is during a certain part of the more winter time, where there's more dark, you're going to see there's an increase in melatonin levels in the hamster. So During the winter, there's long nights, meaning there's more melatonin, so these animals are sleeping more, and that translates or contributes to less testosterone, decreasing the likelihood of seeing any kind of mating behavior. However, as the days start to become longer, like you see from spring into summer, melatonin production decreases because of the dark period gets slower. And what happens is the gonads will now increase in size, and so there's a shorter amount of dark. That means there's less overall melatonin. The gonads increase in size, increasing testosterone, increasing the likelihood of engaging in sexual behavior. And so as the cycle continues, what happens is now the days will start to become shorter from fall into winter, and that decreases the amount of interest in sexual behavior associated with the increasing levels of melatonin and the decreasing amounts of testosterone, and we see that cycle will continue over the course of the year. So not only do we see changes in overall activity level across the day, but we see changes in willingness to engage in sexual behavior across the year related to the length of day. So these are just two examples of periodic changes in behavior that's related to the environmental changes that we have on Earth, related to the length of the day, also related to the length of the year, and those kinds of changes. So the question is, what sets the clock? What's important for keeping these biological clocks in check? And we think that sunlight is an important factor, or a Zeitgeber, something that gives light or gives a mark of when the clock should be started. And if we look at some interesting studies that were done to kind of characterize what are important cues for individuals, what they did is they had individuals looking at when they were most active for a couple of days, and then they transferred them into a bunker where there was no access to light from outdoors. There was no cue about what time of day it was, and they wanted to see what would happen. If you look at our previous example of activity across the day, you can see that even though the lights are coming on or turning off and turning on at certain times, the behavior is clustered to one part of the day. What happens if you take away that turning off and on of lights, or you take away any cues of the length of the day to an organism? What will happen to their behavior? And that's what these bunker experiments set out to do, is to examine what happens if you remove the cues that are associated with the clock or what time of day it is. And what they found was pretty interesting, that as they went into the bunker and there's no cues available of what time of day it was, we see that there's this progressive change across days. Now, they aren't just starting to take naps all throughout the day, so we can see that they still are clustering their behavior around a certain length of time where they're going to be active, indicated by these purple lines. So this is that normal level of activity, that they're up, alert, doing something. One possibility is that it just would be scattered across the full 24 hours, and that doesn't happen. What we see happening is they start to go to bed later and start to wake up later every day. So this is what we refer to as a free-running clock. There's continuous periods of activity, and that period of activity progressively shifts across days, as we can see here. So this individual is showing us a consistent kind of shift over days, where now they're waking up, they're going to sleep later, and they're waking up later every day. Now, after they were returned back to a life where there were Zeitgebers, such as a clock or visual cues outside to indicate time, we see that their schedule normalized back here, and they began to exhibit the same kind of activity during light and dark portions of the cycle. So this bunker experiment illustrates two important points about our circadian rhythms. First of all, there are important information cues coming from our environment that set the clock. But when we remove those clocks, we don't just haphazardly go to bed and take short naps. We still have a bulk of time where we're active, and then the remaining day where we're asleep. So there's got to be something in addition to the Zeitgebers that are coordinating or contributing to the organization of this biological clock. And one other aspect of this, why would we want to look at this bunker experiment? What does this tell us, this free-running clock? And there's some important insights that can be gained from seasonal affective disorder. And as we progress through the year, and we get into fall and summer, what happens is the days get progressively shorter, and it's often overcast, and we don't have access to all those strong cues. We lose some of those Zeitgebers, and we start to engage in a free-running clock. With that, there are certain symptoms that we see, such as sadness, irritability, increased appetite for carbohydrates, earlier sleep onset, and daytime drowsiness. And what they found is by giving those cues, giving those light cues that are missing during those winter months where we have a shorter period of light, what we see is these individuals are able to eliminate or reduce some of these symptoms associated with seasonal affective disorder. So in the bunker, when we completely remove all signs or signals from the environment of when it's time to wake up and go to sleep, we see that free-running clock. In the winter, we're inclined to show some of that free-running behavior, and because our daily schedule doesn't provide for that ability to wake up and go to sleep at a different time, we start to see there are problems associated with that can be manifest as symptoms associated with seasonal affective disorder. Like I said, sadness, irritability. And light therapy has been shown to be effective in some cases where giving that specific Zeitgeber back to entrain that clock can be an important factor in keeping the schedule in place and reduce some of those symptoms. But that's one dimension, of trying to keep the clock set. But what keeps the clock running? Why don't we just take all these little naps? And that suggests that there's another component to the clock that has a neural basis. And we talked about several different pathways within the visual system that play an important role. And one of those pathways that we talked about was the retinohypothalamic. If you remember, that was the pathway that was involved in detecting a color blue in the environment from 460 to 480 nanometers in length. And it's collecting information from the retina and sending that information directly into the suprachiasmatic nucleus. Well, the suprachiasmatic nucleus sits right above the optic chiasm, so it's ready to receive that information, but it's also part of the hypothalamus, that's that regulatory function. What we find is that this suprachiasmatic nucleus is essential or very important for maintaining these biological clocks, the sleep-wake cycle that we see across the day. And if we actually go in and damage the suprachiasmatic nucleus, so we produce damage here and there, what we find is an interesting effect on the circadian rhythm in animals. So here, what we'll see is initially a sleep light cycle here under for rodents, rats, and the heavy bars indicate when the animals are active, and then what happens is they gave lesions to the suprachiasmatic nucleus. And now you don't see any consistent pattern of activity. Here you see a very nice light-dark cycle here with activity that occurs across days. Each one of these lines represents a single day's activity, and then we produce damage to the suprachiasmatic nucleus. And now what we see is here's a day's activity, and the heavier lines represent activity of the animal. And we can see it's scattered throughout. So not only are they not showing any consistent start and stop, but they don't have their behavior confined to one part of the day. So they've lost that entrainment by the environmental cues, and they're not clustered. Well, this study that was done in 1990 by Ralph did something interesting. They took and removed the suprachiasmatic nucleus from one set of animals and then transplanted it back, or transplanted it into animals that had a lesion. So they actually took those neurons there and then put them into the suprachiasmatic nucleus of another group of animals. What they found was quite interesting. After that transplant, there was a reoccurrence of the daily sleep cycle. And you can kind of see that occurring here. There is this pattern where it's free running, so we see that it's free running, but now their behavior, their activity levels are occurring at a certain part of the day, and that's changing across days. So now we start to see that clustering after the transplant occurred. So here's the animals that prior to the lesion, this is their sleep-wake cycles after the lesion. They then transplant suprachiasmatic nucleus from another animal into that lesioned area, and what we see is a little bit afterwards, there is a return to their sleep-wake cycle, demonstrating an important role for the neurons here. While we don't have time to talk about this, there's some evidence that these are actually neurons have a genetic basis of the length of the day. And you can breed animals to have shorter days or longer days. And there's been work that's been done showing that as you replace an animal that may have a 25-hour cycle with an animal's suprachiasmatic nucleus that had a 23-hour cycle, when that's placed into the other animal that had the lesion, that animal will show the 23-hour cycle, demonstrating that there's a genetic basis controlling or contributing to that grouping or segmentation of that sleep-wake cycle. So again, this demonstrates the importance of both environment and neural components to the sleep-wake cycle. So given that, let's talk a little bit more about what we spend a good portion of our time, our lives, engaged in sleeping. And we have to use certain tools to kind of investigate this. And one of the tools that we use is called EEG, or electroencephalogram. This basically records the electrical activity of the brain across the skull. So it's a very non-invasive technique. Maybe you've had a chance to go in for a sleep study, and what they'll do is they'll attach electrodes to your face and to your skull, and they can record that electrical activity. Remember, half of that neural signal within the central nervous system is electrical. The other half is chemical. So that means, just like we saw with the squid axon, you can record that electrical activity. Now, to give you some basis or some understanding of what these signals mean, or what they refer to in terms of states of consciousness, we can see that these are three vastly different states of consciousness. One is alert, actively processing information, and we'll typically see beta waves. Now, what we see here are alpha waves, and these are associated with you're just kind of taking a break, you've closed your eyes, you've relaxed a bit. You're definitely not asleep, so you can still hear information, but you're not processing visual information, you're slowing your breathing, you're a bit drowsy, and you'll see alpha waves. Now, the last kind of state of consciousness that we'll talk about here is deep sleep. This is not, and we'll talk about this, REM sleep, which is distinct. This is very deep sleep. And here we see a vastly different pattern. So how do we characterize what's going on? Well, what I like to do in terms of trying to help people understand EEG and the differences here that we see in these electrical patterns is look at two dimensions. First is how fast the changes are occurring, and what's the amplitude. So like any waveform, you can talk about the frequency. This has very high frequency. These changes are occurring very quickly, but fairly low amplitude. So we see that there aren't any big movements that this graph is making here. So we see there aren't any really big changes. They're all pretty small, fast. So we'd say this is high frequency, low amplitude. I would make an association, or I describe this relationship as being very similar to having 20 TVs on all at once. And each one is tuned to a different channel. And no one channel is winning out. And so you have a lot of noise. You can't focus on that. So there's a lot of change, but there's no one channel that's winning out. So that's kind of like when you're awake. You've got auditory information, you got visual information, you got tactile, touch information, olfactory information that's constantly being processed. As you're sitting here listening to this, you're taking notes. So you're writing on the sheet of paper, you're accessing what I'm saying, you're decoding that information, relating it to what you've learned out about previously, and trying to combine that. That is using a lot of the central nervous system. And so there are a lot of channels active and no channel is winning out. So you see this very high frequency, low amplitude activity in an EEG. Now, as you start to relax, what happens is you start to tune those channels of all those TVs to the same channel. So you have limited information that you're communicating. You close your eyes. The visual system now has been shut off. You start to slow your breathing. You start to clear your mind. And what we see is that now the frequency starts to slow down. We start to see now the needle isn't moving as fast, but because that one channel is winning out, we see larger and larger changes here in amplitude. So the amplitude starts to increase. So here we've removed a lot of processing, a lot of information, and we see that first the amplitude increases, so those few channels now are winning out, and the frequency decreases, so you're not changing as quickly. Now in deep sleep, there are virtually all the channels of those TVs are tuned to the exact same channel, so they're processing just one source of information. And what we see here is that we have very low frequency, but incredibly large changes in amplitude. So here in deep sleep, we're processing no information, these delta waves, and it's just changing very slowly. The frequency is low, but we can have large changes in amplitude that occur. And so that's how you want to look at an EEG and think about it, is, oh, are these small waves and are they occurring very quickly, or are these large waves and they're occurring very slowly? A low state of consciousness, such as deep sleep, as we'll talk about, we tend to see these delta waves. But with a very actively processing situation where you're actively processing information, we'll see some of these beta waves occurring that are high frequency but low amplitude. So let's look at how sleep changes across the different stages. Sleep occurs through stages, and so it's a very dynamic kind of behavior, the way the central nervous system changes. So here what we see is a good example of awake beta rhythm, where it's very high frequency, low amplitude. And then what we see in stage 1 is where we have some of this high frequency. So it's a little bit less frequency, but it's still low amplitude going on in stage 1. So we're still actively kind of processing information. But as we start to drift into stage 2 sleep, what we see is the occurrence of two things. First of all, sleep spindles and K complexes. These are unique kind of electrophysiological characteristics that are recorded in an EEG that indicate the person is starting to eliminate some of those external sources of information, such as sounds in the environment, and trying to get that person to remain asleep. What's interesting that we see these sleep spindles and K complexes decrease as a person ages, so that over time there is a reduction in sleep spindles and K complexes, those things that keep an individual asleep. And one of the things we see is that as people age, they tend to sleep less, or they're more easily awoken. Now, as we get into stage 3 and stage 4 sleep, there's a progression further away from high frequency, small amplitude, to where there's a higher prevalence here of large waves, and then delta rhythms, like we see here, very characteristic of the stage 4 sleep. This is that deep sleep we're talking about, where it's little to no information is being processed. We have large amplitude changes associated with very slow frequency. Now, our deepest stage of sleep is REM sleep. And REM sleep is denoted by rapid eye movements. So during these other non-REM stages, we will not see these rapid eye movements occurring. During REM sleep, what we'll see is, first of all, an immediate change to high frequency, low amplitude electrical and physiological activity recorded, and rapid eye movements. The eye movements will dart back and forth very quickly. I've included a link to a Scientific American video in Blackboard under the content for this chapter, and it shows a sleep study, and you'll be able to see some of those rapid eye movements when they enter into REM sleep as the person's going through the sleep study. So you want to go through and watch that video. It's pretty good. I would show it here, but it doesn't capture that well in the Collaborate, so I'm just going to refer to it, but you should go watch it, and I'll bring that video up again later on in this lecture. But you'll be able to see some of those random eye movements. So what we want to do then is see, well, across the night of sleep, what happens? How do we transition through these? What happens? And it's pretty intriguing. What happens is that we're awake, and then we start to go to sleep. And the first thing we'll do is enter into stage 1 sleep, 2, and then 3. We'll go into stage 4 a little bit, and then we'll cycle back up into 3, 2, and then just as we're getting ready, we'll drop into a little bit of REM sleep. And then we'll cycle back down to 2, 3, 4, 3, 2, then we'll go into a little bit longer REM sleep. So on the y-axis, we have time of the night. So you go to bed and you'll sleep for approximately 8 hours. And as we progress across the night, what we see is that we cycle through these periods of sleep. So here on the x-axis is stage 4, stage 3, stage 2, stage 1, and awake. And we're indicating REM as being very similar to awake because those patterns are very similar. So we see that you'll start here in stage 1, 2, 3, 4, 3, 4, 3, 2, REM, 2, 3, 4, 3, 2, REM. And as the night progresses, what we see is an individual will actually spend more and more time in those lower stages of sleep. And we see later on in the night, there's a lot more time spent in that stage 2 sleep and transitioning from 2 to REM sleep, to finally when you wake up. So we can characterize that across the night. where you start out spending a lot of time in these different stages, and then finally there's a dominant REM sleep pattern that occurs later as you're sleeping there, where you're spending a lot of time in that REM sleep, or you see those random eye movements. So we see this change across the night. How does this change across the lifespan? Well, what you'll notice is that very young age, from 1 to 10, we spend a bulk of our time here. Well, actually, from birth to 1 year, we spend a great portion of our time sleeping overall. And almost half of our time is spent in REM sleep. As we go from 1 to 10, to 30 years, to 60, and so on, we see the amount of time that we spend in REM sleep progressively decreases. And after 10 years of age, overall, we're spending progressively less time sleeping. We can see that even in our 30s, we're starting to dip down below 8 hours of sleep to where it's far less as we're going across here. And a lot less of that time is dominated by REM sleep. So across the lifespan, there's a dramatic change in the amount of time that we spend sleeping. Considering this, what are the distinguishing features beyond this random eye movements from non-REM sleep? And what we can see is that in non-REM sleep, you often see movement. So when you're in those lighter or earlier stages of sleep that's considered non-REM sleep, we'll get a lot of movement. So as you're turning in bed or something like that, or talking, you're in non-REM sleep. If someone wakes you during that period that you're in one of those non-REM stages of sleep, you often report maybe static images or ideas, concepts. It's not very dynamic. In contrast, REM sleep, you'll see that there will be complete paralysis. So during REM sleep, you're completely paralyzed. The author of your textbook, Ian Wishaw, had a horse, and this is his horse, and while it was in this non-REM sleep stage. And what we see is that horses will lock their knees, and they'll be in this non-REM stage. But as soon as they start to go into REM sleep, they'll relax, go down on their knees, lay on their side, and they'll be completely paralyzed while they're in that REM stage here. So that's what we're kind of seeing, the paralysis. So you can still see movement and other things during non-REM sleep. During REM sleep, we see complete paralysis. Now, if we wake somebody while they're in that REM sleep, they'll report very vivid dreams that have narrative content. That's where those strong, bizarre dreams that maybe you've woken up while you're in REM sleep and you'll tell your friends the next day, I had this strange dream. The video that we have from Scientific American describes some of what's going on with those dreams. I won't talk much about dreams here about this, and because it's hard to study them in any systematic fashion, but we can kind of study what they may be responsible for or what they're associated with. And we'll talk about that when we talk about theories of sleep. But what is distinguishing non-REM sleep from REM sleep, during REM sleep you're completely paralyzed, you have those random eye movements, and if you're woken you'll have these very vivid dreams that have narrative content. During non-REM sleep you're not paralyzed, you'll often talk, or you'll be able to move, and if woken you'll have these very static kind of dream or reports of what was happening. So why do we spend so much of our life engaged in sleep? And there's a variety of kind of theories or possible factors contributing to this. One early theory suggested that sleep was really just a passive process, because our environment, our world goes from a light to a dark period, and since there are fewer stimuli under dark conditions, you go to sleep because it's not as interesting. That's the basic idea. So lack of stimulation puts you to sleep. This is flawed, or this has several limitations or evidence against this perspective. First of all, when you actively put people through sensory deprivation, they sleep significantly less. So if you restrict their access to environmental cues, auditory, visual, tactile, these people will sleep less. So it's not just that not much is going on when it's dark out, so I'll go to sleep. Sleep is a very active process, as we can see that you transition through stages of sleep that are very different, such as the REM and non-REM sleep that have very different components or characteristics. So it's not just purely a passive process. And in addition, there are many nocturnal animals as well that are awake during the night. And so that idea of sleep is just a simple passive process. Doesn't provide much context to further experimentation or explain the behaviors that we see. Another kind of, and here's a good example of that, animals that are nocturnal animals, we can see that they're up and active under dark conditions. So it's not just, there isn't much going on. Another perspective that people have had that may contribute to this, that sleep has an adaptive value. That while you're sleeping, you conserve much less energy. So in those situations, sleeping for a longer amount of time may be an important aspect of conserving energy. It may be a situation where, because of the environment that an animal is in, if they're a prey animal, they may need to be alert much more than an animal that is at the top of the food chain. And we can see here, for example, that there is this change across these organisms where there are vastly different amounts of time that these organisms spend sleeping. And it's something about their where they are in their niche that can determine what their home or their place in their environment, their niche, is involved in that. And we can see here a great range in the amount of time spent sleeping. So trying to say that somehow it's related to risk of predation as an adaptive value, we can see across these different animals there's different amounts of risk of predation, but they're sleeping for different amounts of time. So this doesn't exactly fit with that. I mean, there could be something associated with both risk of predation and conserving energy, but there are some animals, or one limitation to this adaptive value, there are some animals that should never sleep because of how hostile or variable their environment is. For example, dolphins that are constantly swimming in the Ganges River, that is a very muddy river that's dangerous, should not sleep. Yet, in fact, we see that they've evolved a very interesting solution where their hemispheres alternate sleeping. So one hemisphere is awake, while the other hemisphere will show us those different stages of sleep, going through that sleep. So apparently sleep isn't just to preserve an animal or be just influence their energy conservation or related to potential being subject to predation, but there's something else that sleep is offering. That organisms can, that's important for the survival of an organism. And one idea is that maybe it serves a function, and here's one of those dolphins in the Ganges River that will alternate hemispheres so that one hemisphere go to sleep as the other one is awake. So even though it's a very hostile environment, and why can't this animal just evolve to not sleep, just be consistently processing, it's adopted a very interesting kind of pattern or behavior, physiological response to this environment so that sleep can still occur. One possibility is it's serving as a restorative function. So what happens if you start to deprive animals of sleep? Well, this study used an apparatus where you had two animals on a turntable. one was connected so we could record from the animal and detect when it would start entering sleep cycles by the EEG. And as soon as that happened, what would happen is the table would start to turn on the animal. And specifically eliminating the animal, because if the animal didn't wake up, it would fall into this very shallow pan of water. Whereas this other animal, it could sleep or whatever, it would still turn, so to get all the experience of being in this apparatus, having the table turn, falling into the water, but it was not receiving the specific disruption of sleep. And so what you find is the animal that was selectively deprived of sleep became sick very quickly. Within several days, we see the animal's health deteriorates, the animal will stop grooming, and it will start looking very sickly and can't move as quickly. So maybe sleep plays an important process in terms of restoring function. So sleep deprivation, humans will become sick very quickly. Another thing that's interesting that we've seen is if you selectively deprive an animal of REM sleep, that they'll often show REM rebound. That means that the amount of REM that you've deprived them for will be caught up or recaptured on subsequent nights of sleeping. So it's like there's a bank or a general checking ledger of the number or the amount of REM sleep that you need, and there is a rebound that occurs across nights. So if you deprive somebody of REM sleep over multiple nights, you'll often see that they'll spend far more time, they'll enter REM sleep much quicker on subsequent nights and stay within REM sleep much longer to make up for that lost REM sleep. Also providing evidence for that restorative function of sleep, and specifically REM sleep. Now, what kinds of functions would constitute this restorative kind of function? And one thing that people have gotten pretty interested in and looking at is this idea that maybe it plays a role in formation of memories or memory storage. One study, what they were able to do was record from neurons within the brains of rats as they were sleeping. And what these black dots represent are individual neurons, and what the lines represent is some paired firing. So these meant these neurons that we're recording from were firing at the same time. As these lines get thicker, like we see here, these two lines, that means these two neurons were paired in their firing characteristics. These were paired to some degree, these were paired, so these suggest these neurons were firing. This is what they initially observed in rats before they were introduced to a behavioral task. So the night before they were to be tested, they saw this pattern of activity of all of these neurons. We see that there was some type of pattern of firing. Now, as an animal was actively moving through the environment, what we see is that there's this pattern of movement that occurred in the environment, and these neurons were correlated in their firing. So we see that there was this very distinct pattern. You could almost imagine a rat walking through an environment searching for food, and as it goes from one place, this neuron turns on, this neuron turns on, then this neuron, those turn off, this neuron turns on, this neuron turns on. And each one of these heavy lines represent a correlated firing of these neurons as an animal is walking through an environment, almost like generating a digital record of where they've been in space. Now we see that this pattern is very different from what was observed when they were sleeping before. What happens the night after the first time they walked through that environment and were searching for food? What happens? During sleep, we see that that pattern is replayed almost to the same degree as what we see when the animal was engaged moving through the environment. There's a great deal of similarity here in this firing pattern or the correlation between these individual neurons that we see during the actual behavior of moving through the environment, suggesting that there is a replay of these neurons, this pattern of neural activity, while they're asleep, suggesting that this brain structure that this was observed in the hippocampus is playing an important role in memory formation. And we talked about the hippocampus. It's a structure, when damaged, causes this very persistent amnesia where people cannot encode or learn new information. In addition, that's a structure that's damaged in Alzheimer's disease. And so it's interesting that we see the neurons, the way they fire when an animal is walking around an environment, and are replayed while they're asleep on that subsequent night. And this is very different from what we see during sleep prior to that behavioral task. So is there any evidence that we see this in humans? Well, one study looked at this using a brain imaging kind of task, looking at as a person was doing a serial reaction time task. So what they have to do here basically is a light will turn on and they have to go and touch a button associated with the light. Another light will turn on and then they have to go touch that button. And so they have to learn to press a button associated with all these different lights. Typically there can be anywhere from 5 to 8 lights and 8 buttons, and they'll have to learn to push the button for each light and try to get as quick as possible. Well, as they're doing the serial reaction time task and getting better, we can see both the occipital lobe as well as that parietal lobe. So this is that, we talked about that dorsal stream using visual information to guide movement is activated. Well, what happens when they go to sleep after learning the serial reaction time task? Well, what we see is that those same centers, those same areas are active during that night's sleep. So that dorsal pathway that was engaged while they were doing that serial reaction time task now is reactivated and active during that night, during REM sleep. So that provides evidence that, further evidence that maybe part of that restorative process is encoding those day's activities. Now, the video that we have in Blackboard under content looks at this idea and gives some additional kind of evidence to support that while you're asleep, you're encoding memories from that day's activity. So you should go through, look at it. It's really pretty strong evidence, additional evidence that while we're sleeping, during REM sleep, we seem to be processing information from that day's activities and using it to form those memories. So, given this, what are some problems associated with sleep? We'll talk about 3 general types of classes of disorders. First, we'll talk about insomnia. Then we'll talk about disorders associated with REM sleep, and then we'll talk about disorders associated with non-REM sleep. The first major sleep disorder that many people suffer from occasionally is insomnia. And this is, and I have to be very clear on this, this is a symptom and not a disease. So you don't just have insomnia. Insomnia can result from a variety of factors, including taking sleep medication or other types of medication that could interfere with sleep. Stress could also cause insomnia. So insomnia is not a disease itself. It's a symptom of something else is wrong. Another very strong factor that can result in insomnia is sleep apnea. That tendency in terms of to be sleeping and then not being able to breathe at the same time. And that can come from different kinds of factors, including the throat and other things collapsing as you're going to sleep. This is a typical pattern of sleep overnight. What we see here is an individual that's sleeping over the night. Again, REM sleep is indicated here. We see that they're spending progressively more time in REM sleep. And here is the wakefulness here, stage 1, stage 2. And And so we can see that occurring in a normal person. This is the sleep profile of somebody that has sleep apnea, and we can see a vastly different kind of pattern where they spend a lot of time awake. They spend some time in sleep, stage 1, and only a brief period enters this REM period here. So this is somebody that has sleep apnea. This is a person that doesn't have sleep apnea, and we can see that that sleep pattern has dramatically changed for these individuals. So they continue to, as they stop breathing, they wake themselves up. And so this is a good example of that, kind of staying awake due to some factor. But taking certain medications and sleeping medication itself while you may sleep, one night you develop tolerance to it, and so there's something else that's going on that's causing the insomnia, and that's only treating the symptoms. It's not getting at the core basis of that. Next, we'll turn to some REM sleep disorders. One that you may have experienced, and I haven't had this experience before, but oftentimes when I ask classes about it, they'll say they've definitely had this. One's called sleep paralysis. That's where, as you're starting to wake up in the morning, you find yourself completely awake, but you're unable to move. And that's because the systems that are recruited to make you paralyzed during REM sleep are still just a little sluggish to turn off or to become inhibited. So that sleep paralysis is still in effect, and so you wake up, but you can't move. So it's a continued inhibition of these motor neurons that occur during REM sleep. Now you can also have this system, this paralysis system, come online suddenly while you're awake, and that often occurs during, or it can occur during narcolepsy, where a person will suddenly collapse, and that's activation of this paralysis system that occurs during your occurring while you're awake, and you can see this cataplexy where they'll suddenly collapse in terms of the system. So this is an activation of that system that keeps you paralyzed during REM sleep. And as you can imagine, we can have also the other situation where you can go to sleep in a REM sleep, but because that motor system isn't activated, you can have REM without atonia. And so there are cases where people will actually act out their dreams. So somebody who plays football is dreaming of playing football, and they'll get up during REM sleep and actually tackle the lampstand or run around the room. So there are rare cases of that where there's REM without atonia that have been documented. Now during non-REM sleep, there are several things that we can see. First, a lot are associated with children, where we see these kinds of disorders occurring with non-REM disorders. Nocturnal enuresis is bedwetting, and that typically occurs during non-REM sleep. One of the good things is this can often be treated very easily and gradually training the system to learn those cues to wake oneself up. So that is a non-REM sleep. Sleepwalking is another example. So it's not REM without atonia, because if you wake people up while they're sleepwalking, you'll see that they are actually in those lighter stages of sleep, and they're not in REM sleep. They won't record or be able to report any kind of narrativity like that. So sleepwalking occurs often very young in younger individuals. And our last one is night terrors. That's also occurring during non-REM sleep. Oftentimes, people will report waking up and this sudden, severe amount of dread or anxiety with no real narrative component to it. Children will wake up screaming very loud, and what you see is that is associated with these non-REM phase of sleep. They're occurring. Both sleepwalking and night terrors will resolve on their own, as does typically bedwetting, or it can be treated very effectively as well. But these all reflect certain disorders associated with sleep, non-REM sleep. Okay, this concludes our last section of the third unit, sleep. So what you want to do is make sure that you review all of our sections here that we talked about. We started this section talking about this unit started with development, and then we talked about the visual system. We talked about those factors that influence behavior, such as emotion, motivation, and then we concluded with sleep. So you want to review these notes. You want to review those practice exams and the lecture quizzes, and then you'll be prepared to take Unit 3 exam, and then that will conclude this class. You'll also want to make sure that you've been working on and you've got your mechanism of action blog. That's the other kind of component of your grade. And just to remind you that your grade is based on the 3 exams that we have in here, which is 20, each one is 20%. Your lecture quizzes, that's worth 15% in total. Your score on those, your average, total score on those. Your practice exams is worth 15%, and your mechanism of action blog is worth 10%. And good luck, and I hope you enjoyed this class and take something away. Remember, you should go into content and look at some of those links. Those videos are very good, and I may add additional ones as I come through it. Talk to you later. Bye.